Hi everybody, welcome to another video in Trigonometry, section 1.5, fundamental trigonometric identities. These identities are fundamental. Of course, there will be a lot more of this. Right, so this just from the definition. I should remember definition, talking about definition, we have this. Sine cosecant y over r over y, so that just flip the reciprocal of the other. So cosine, sine and cosecant, cosine, secant, tangent and cotangent are reciprocal of each other. Now, next we have the quotient identity. Tangent is sine over cosine and cotangent is cosine over sine. So why is that? We just said, like I said, every identity here is fundamental because we just use a definition. So tangent is y over x, right? How about sine over cosine? Sine is y over r, cosine is x over r. Divide fraction is multiplied with reciprocal, so this is equal to y over r times r over x. R cancel out, we have y over x. So tangent is y over x. Sine over cosine is also y over x, so that's why it's good. I said there's a trick to memorize all of this. Pythagorean theorem. Sine square plus cosine square equal to 1. By the way, when we write sine square, we mean sine and then square. We're not doing the square of the angle first. We never write like, usually the angle square doesn't appear much in trigonometry. Usually the square is here where we check the sine first and then we square. Right, so that don't have enough space, but I'm going to write here. We have sine square plus cosine square is equal to 1. So sine is y over r, we square that. Cosine x over r, we square that. Now give us y square over r square and x square over r square. Both of them have r square at the bottom. X square plus y square on the top. X square plus y square by Pythagorean theorem. X square plus y square equal to r square. So r square over r square is equal to 1. So that's why sine square plus cosine square is equal to 1. And then there's the other, which we'll prove similarly. Right. Now, I found this on the internet. I don't remember, but it's called the Hexagon Trick. You will see different variation of that. I think this will be the best one. So, how to form the hexagon trick? So what we do is we draw the hexagon. With the pointy top and bottom. Of course, hexagon, we divide that into 6. Right? Put tangent on the top and followed by sine and cosine. After that, we use the reciprocal identity. Tangent is 1 over cotangent, so cotangent and tangent will be opposite to each other. Sine and cosecant opposite to each other, and cosine and secant opposite to each other. At the middle, I will have 1. Yeah, so that hexagon trick, simple enough, right? Tangent on the top, then sine, cosine. Right, so how did that help? With this, we'll take care of all of these identities that we have here. So think about this. If we have tangent on the top, it will equal to 3 ratio here. Tangent is equal to tangent over sine, sine over cosine, 1 over cotangent, and secant over cosecant. Right? If we put tangent on the top, that's what we have. Right? Now, so we can say tangent equal to, if we put tangent on the top, you can see there are 3 sine over cosine, 1 over cotangent, and secant over cosecant. That's the quotient identity. 1 over cotangent, that reciprocal identity, and we have secant over cosecant, which is correct, but we don't have the name for it. Right, so that's going to, of course, rotate. Let's put cosine on the top. If we have cosine on the top, then cosine equal to cotangent over cosecant. One over secant, and sine over tangent. Right? So whenever we rotate whatever function on the top, we have 3 ratio, 1, 2, and 3. That will be a lot more than the identity we have here. So that gives us the ratio, the quotient identity and reciprocal identity. And then also, when we write like this, we also get the Pythagorean identity. So with tangent on the top, we have 1. We can draw up and to the left. So cosine square plus sine square is 1. 1 square plus tangent square, secant square, and cotangent square plus 1 is equal to cosecant square. When we follow that arrow. So let's see, if we're talking about this arrow, we have cosine square plus sine square equal to 1. And if we follow this angle, this arrow, 1 square, we don't need to write 1 square, do we? 1 square is still 1, right? 1 plus tangent square is secant square. Yeah, so up to the left. With that, there's a way to memorize all of those identities. And having said that, these identities are called simple because, are called fundamental because it's just based on the definition. Alright, next, assume sine is equal to 3 over 4. What is cosecant? Alright, take a look at the hexagon. What is sine and cosecant related? How are they related? Opposite from each other from a hexagon, meaning it is reciprocal. So put cosecant on the top. Cosecant is 1 over sine. So we have 1 over 3 over 4. Divide by fraction is multiplied with reciprocal. So that's 4 over 3. Enough. It's simple enough. Now, knowing sine and cosine, find out tangent and cotangent. So first, tangent. So put tangent on the top. We know sine, cosine, right? So tangent on the top, tangent is equal to sine over cosine. So sine is 3/5. Cosine is negative 4/5. Multiply reciprocal. I will flip this. 5 divided by negative 4. So that gives us negative 3 over 4. How about cotangent? Cotangent is cosine over sine. Right? Cotangent is cosine over sine, but also 1 over tangent. So it's much better we just use 1 over tangent. So 1 over tangent is this. So we just flip them. That's what we have. Next, if tangent is 4 and secant is negative, find secant and sine. Right? So we have tangent, right? And secant. So what is the relation of secant and tangent? Well, 1 plus tangent square is equal to secant square. So certainly we can solve for tangent secant, right? So secant, 1 tangent is 4. So secant square is that 1 plus 4 square is 16, 17. So secant square is 17. To solve for secant, we take the square root on both sides. And every time we take the square root on both sides, don't forget there's a plus or minus. So secant is going to be equal to, plus or minus square root of 17. And since the question says it is less than 0, it is negative square root of 17. So that gives us secant, negative square root of 17. Right, then how do we find sine? Okay, let's look at this. We want to find sine, right? Put sine on the top. It is tangent, which we know, over secant, which we also know. So sine, according to this, tangent over secant. For secant. So yeah. Yeah, let's just write negative 4 over square root of 17. Right, that certainly works. So we used all the identities, the fundamental identities, we can do that. But like I said, back in section 1.3, we can just use definition, right? So I will do this differently. I don't have enough space, so I just have to write on this note card here. So there's another way to do this, just using definition. Right, so what we know, tangent is equal to 4, right? And then secant is negative. Right, how do we do this? We can just use definition. And by definition, I mean if we know x, y, and r, we can know the rest. We can know all the trig function, right? So try to determine x, y, and r. But first, secant. What is secant? Secant is r over x. So we start with this. The first step is we look at the secant. Remember, I did mention that in section 1.3, I prefer to work with sine, cosine, secant, and cosecant because those ratios have r in it, and r can only be positive. So it is easier to work with some that is not tangent or cotangent. So first, secant is r over x. We know for sure r always positive. X we don't know. But since it's negative, since less than 0, not theta. Sorry. Oh, that one was running out. since it's less than 0, it's negative. Now, if it's like this, x have to be negative. Right. So don't go by tangent and cotangent. If we have something else, try that, and we just try that. Next, we go to tangent. It's 4, right? Now, what is the ratio for tangent? Tangent is y over x. I hope you memorize it by now. If not, in the next section, there's a way to further help you to memorize all of that. Right, y over x. What we know, x is negative, right? So what is y? Whatever it is, the ratio here has to be 4, which is positive. Because of that, y is negative as well. Yeah, always try to work with something that doesn't have tangent or cotangent, because tangent and cotangent does not have r, and the size we don't know. Right, and finally tangent is y over x, and it is going to be equal to 4, but I will write 4 over 1. Instead of 4, I can write 4 over 1, right? And then x is negative, y is negative, so I'm going to choose both of them to be negative. So with this, x is equal to negative 4, y is equal to negative 1, and r square root of x squared plus y squared. So give us square root of 17. It's always positive. It's always positive. Right, square of 17. We have x, y, and r. The rest is easy. The question wants us to find secant which is r over x. R over x. And then sine y over r. Yeah, because I wrote this backwards. X is negative 1, y is negative 4. Sorry. So we have negative 4 over square root of 17. Yeah. So we can always do, when we talk about trigonometric function values, when we try and find this, if we can go back to x, y, r, it always works. We don't have to use those identities. If we don't need to, we can always do this. Once we know x, y, and r, we know all the tricks values. Right. Look at that one more time. Right. So next we will simplify this trigonometric function values. Now this is not easy. There's a lot of things we can do. Oh, sorry. We still have that example, which we haven't yet to. Right, sine is equal to 1 over 3. Cosine is less than 0. Find cosine. So, of course, you can use the x, y, r, the definition, or you can use the identity matrix, identity from the hexagon here. So sine and cosine next to each other, there is the Betown identity. So cosine square plus sine square is 1. So we have sine square, we just need to find cosine square. 1 minus sine square. Sine is 1/3 square. 1 square is 1, 3 square is 9, so we have 8 over 9. Right. And then cosine square is equal to 8 over 9. to solve for cosine, we take the square root, and every time we take the square root on both sides, don't forget it's a plus or minus. So it's plus or minus square root of 8 over square root of 9. I just split the square root, and so we have square root of 8, square root of 9, 3. Square root of 8 you can write as square root of 4 times 2, or square root of 4 square root of 2, or 2 square root of 2. If you want to, you can write 2 square root of 2 instead. Well, don't have to. But what we need to do though, cosine is negative, so this is negative square of 8 over 3. So the answer is negative. Of course, if you don't want to use the identity, you can always use the definition with x, y, and r. But when we have sine, cosine, tangent, and secant, or cosecant and cotangent, use Pythagorean identity. Right. Next, we're going to simplify some trigonometric expression. It's not easy. Right. First, cotangent plus tangent. What's that? And then cosecant times secant. Right. So when all fails, or I mean, if you don't know where to start, I should lead with that. If you know where to start, it will be a nice thing if we put everything in terms of sine and cosine. Right, cotangent. In terms of sine, cosine, it is cosine over sine. Tangent, sine over cosine. Cosecant is secant over tangent. We're not going to use that, but we use 1 over sine. Secant, 1 over cosine. Right. If you don't know where to start, put everything in sine, cosine. Right. Now, common denominator of sine and cosine. Right. So sine, cosine is a common denominator. So we try to get sine, cosine at the bottom. This one has sine already. It will multiply a cosine to it, top and bottom. So in that case, we have sine, cosine at the bottom. So the top cosine square plus cosine square, cosine times cosine is cosine square. Next, already have cosine, we need another sine. So that gives us sine square. Cosine, sine at the bottom, common denominator, and then plus 1. And then cosine square plus sine square together is 1. So we have 1 plus 1 on the top, sine and cosine. So that is 2 sine over cosine. I mean sine, 2 over sine cosine. Right. And we can write as this 2 on in front, 1 over sine, and 1 over cosine. 1 over sine is cosecant. 1 over cosine is secant. So that's simplified. Of course, usually simplifying, we don't know where to stop. If it's not obvious like this, you can say, yeah, that's good enough, or that's good enough. Yeah. Sometimes it's nice, and we know exactly what it is, but sometimes it's not obvious, then we just stop it whenever it looks more simplified. I guess. Right. Now, this one already in sine cosine, which is good. Go straight from here, multiply them out. Cosine times cosine. Cosine times cosine is cosine square. Cosine times -1 minus cosine. Cosine times 1. And 1 minus 1 is 1 times -1 is -1. Then plus sine square. So I just multiply this out. First outer, inner, last. Negative cosine, cosine cancel out. And we have cosine square -1 plus sine square. Right. Just like the previous example, cosine square plus sine square equal to 1. So sine square, cosine square, it is 1. And we have 1 minus 1, so this is 0. So no argument there. 0 is the simplest form, so there's no confusion here. If it is extremely simplified like this, then that's the answer. Whereas those two, yeah, debatable which one is more simplified than the other. Right. Like I said, if you don't know where to start, just write everything in sine cosine. That usually is a good way to start the problem. Tangent here. Tangent in terms of sine cosine is sine over cosine, right? Cotangent is cosine over sine. Right? Now let's multiply them out. That times that. So that's times the first one and then times the second. That cancel out. That cancel out. Sine square plus cosine square, because we've seen that a few times. Pythagorean theorem, Pythagorean identity, which is equal to 1. Of course, do the same thing. So that's why I usually prefer to change to everything to sine cosine. It will be more obvious that when we see the Pythagorean identity, we know that sine square plus cosine square is 1. Even though for something like this, it will be more complicated if we go with sine cosine. But nevertheless, this one, change to sine cosine, is not the best way, but it still works. So we still do it that. Secant minus tangent. Secant is 1 over cosine. Tangent, sine over cosine. That's not that bad. Secant 1, and this is a plus. Sorry. So we have a one big fraction. I mean two big fractions. Right, one on the top. Next, the bottom though, both of them have cosine, so we'll write common denominator of cosine, and we have 1 minus sine. The other one is 1 plus sine over cosine. Right. Now divide fraction is multiply reciprocal, right? So we have cosine. Just flip this 1 minus sine plus cosine 1 plus cosine 1 plus sine, sorry. Alright, this doesn't really help for here, but what we can do here is common denominator of those two. Yeah, on this one, if we write sine cosine may not be the best option, but let's just say an easy option. Right, now to get to the common denominator of this, already have 1 minus sine, so we need the 1 plus sine on the top. And then plus cosine. Already have 1 plus sine, it's missing the 1 minus sine, so that be 1 minus sine. Right, now just multiply all out and try to simplify. At the bottom, 1 times 1 plus sine theta minus sine theta minus sine square. The top, cosine times sine cosine minus cosine times sine. Right. We have sine cancel out. Those cancel out. And cosine plus cosine, there will be 2 cosine on the top. And here we have 1 minus sine square. So what's that? So that's the reason I prefer to write everything in terms of sine cosine, because when we see the sine square, cosine square, more often than not, it is Pythagorean identity. So the Pythagorean identity is that. So if we want sine, just subtract the cosine on the other side. So from here we can say sine square is equal to 1 minus cosine square. Or if we want to, we can subtract sine on the other side, so we have cosine square is 1 minus sine square. Yeah, so we can use this as well. And here we have cosine square is 1 minus sine square. So yeah, the bottom here is cosine square. So we have 2 cosine over cosine square, and one of the cosine cancel out. We end up with 2 over cosine, and 2 over cosine is reciprocal cosine secant, so this is end up to be 2 secant. Sorry, pronounce space, but that is 2 secant of theta. Of course, if we can go straight forward using secant and tangent, it will be a lot easier, a lot more elegant. But like I said, if you know where to start, the good way to start is write everything in sine cosine. Might not be the best option, but it will work more often than not. Right. When we go to chapter 5, we spend a lot of time proving identities, a lot more identities than just this. But for now, just do some basic things. And the basic thing is trying to write in terms of sine, cosine, see what happens. Right, so those are identities. Now, the remaining of the section, we prove something that is not an identity. So, to prove identities, a lot more difficult. But if we want to show that it is not identities, all we need to do is just find one counterexample. Only need one counterexample. So, just like if you are in a court and they try to find you guilty of something, if you can show that you are not there at the time, that is like one counterexample, that will be enough. Then they cannot say you are guilty. If you can prove that you are not there at the same time, so that is kind of like the counterexample. If you have an alibi, that's good enough. So, same thing here. If there's one counterexample that it doesn't work, it cannot be identity. Identity means it works for every values of theta, every values of the variables. Right. So how do we find that counterexample? Well, that not an easy thing. One way to do that though is we just graph them and see if we have identities, the graph should be identical, right? Now, by the way, we have in degree mode, which is good. If we have degree mode, make sure we change the windows. Let's say we go from 0 to 360 degrees. And in that case, let's mark each one of them like 90 degrees. So 90-degree increment. Once again, if we graph using degrees, change the windows from 0 to 360, something like that. Right. Now I will graph the two functions. Sine, theta, just use x, doesn't matter. Cosine, variable, square. So that's the first one. And then the second one is sine square plus the square of cosine. Right, let's see the graph. Right, one function look like that. The other function look like that, which is 1. Because this is equal to 1. So we prove that this is not identity, meaning that we show that this is not always equal to 1. So we look on the graph where it's not equal to 1. Well, we see that somewhere below, between here, like 45 degrees, right? Because 90-degree increment, so this would be 45 degrees. So let's say at 45 degree, sine of 45 degree plus cosine 45 degree square, sine 45 degrees, 45 degrees square of 2 over 2 plus square root of 2 over 2. So that gives us 2 at the bottom, common denominator. The top, 2 square root of 2. 2 and 2 cancel out. And that is equal to 2. So you see the graph, indeed it is equal to 2 at 45 degrees. So the left hand side at 45 degrees, it is equal to 2. So at theta equal to 45 degrees, left hand side equal to 2, but the right hand side equal to 1. So that's why it's not identity. Identity have to work for all the values of theta. Right, next one we have sine of 2 theta and then 2 of sine theta. Right. Sine of 2 theta look like that, and 2 sine theta look like that. So what you see, the graph are not the same, except for those 1, 2, and those points. But it here, that's 90 degrees, right? Yeah. So increment is 90 degrees. So we just find a counter example at 90 degrees. The left hand side, sine of 2 times 90 degrees, sine of 180 degrees, which is 0. The right hand side is 2 sine of 90 degrees. Sine of 90 degrees is 1, right? Yeah. So 4 fingers, square root of 4 divided by 2. 2 over 2 is 1. So at 90 degrees, the left hand side is equal to 0, the right hand side is equal to 2. They're not the same, so not identity. Yeah. One counter example can show that it is not an identity. If we want to prove it is an identity, we cannot just choose the values like this. We have to actually prove to work or prove that it is identity so that it works for all values of theta. But like I said, that is chapter 5. Right now, this section, just get familiar with these identities, which can be summarized in the hexagon. So I have this along with those formulas. I keep that for future reference. But in this section, like I said, get familiar with the identities and the manipulation here. We're going to do a lot more of this in chapter 5. But one thing that I usually do is write everything in terms of sine, cosine, and we go from there. Right. So this is section 1.5 in trigonometry. Thank you for watching.